student from the Utopia group at UT Austin. In this talk, I will present our recent work, program synthesis using abstraction refinement. This is a joint work with Isil Dillig and Rishabh Singh. So first of all, from a high level, this talk will be about programming by example. So for those of you who are not so familiar with this, the goal of programming by example is to construct a program automatically that satisfies the given specification, expressed as input of examples. So this is a very hot topic that has found many applications in various domains. For example, it has been used for automating string transformations, table transformations, data imputation, and automatically generating SQL queries. As you can also witness from the sheer amount of papers published on this topic in recent years, building an efficient synthesizer for a new domain from scratch is not at all an easy task. So our goal in this work is to make it much easier to build domain-specific synthesis tools. In particular, we have proposed a meta-synthesis technique that can be instantiated to any domain with a little bit of guidance from the domain expert. So that is, the domain expert just needs to instantiate our meta-synthesizer with some domain knowledge, and the generated synthesizer can be reused across many use cases by lots of end users. So in addition to being applicable to a broader range of application domains, we also want our meta-synthesizer to be scalable, that it can scale to larger search spaces. So before showing you our key idea that allows us to achieve both of these two goals, I'm going to first very briefly tell you a common trick that is widely used in existing synthesis algorithms for improving the efficiency or performance. So the idea in this trick, roughly speaking, is that it partitions the program space, the universe of all possible programs, into equivalent classes based on the program's input-output behavior, such that programs belonging to the same partition produce the same output value on the given input example. So this idea is very useful because it essentially reduces the search space. For instance, if you consider using this trick in an enumeration-based algorithm, then basically it says is you basically reduce the number of programs you need to enumerate, because whenever you reject the program, you can also reject automatically all the programs belonging to the same partition. Okay, so in other words, this trick helps. Using this trick, the algorithm only needs to look at one program for each partition. So as you can see, these techniques based on this trick scale according to the number of concrete values that can be produced by the programs in the space. And as you can also imagine, this technique will not scale well if the number of values becomes very large. So in this work, we propose a more scalable synthesis technique. Our key idea is to partition the program space based on the program's abstract input-output behaviors. So in particular, let's say we have an abstraction with only 3 abstract values. So by the way, the abstract values here are abstracting the output values of programs. So we have 3 abstract values. We're going to partition the program space into 3 equivalent classes, so that programs in the partition I produce the value phi I. All right. So the advantage of this technique is that it can reject many programs all at once without needing to look at the concrete values that can be produced by the programs in this partition. And this helps us to achieve a more significant search space reduction compared to the idea of using a partitioning using concrete input-output behaviors. So for instance, if we know that the output example O is not in the concretization of the abstract value phi2, then we can immediately reject all the programs in this gray partition at once. Okay, so based on this intuition, we introduce a new kind of synthesizer, which we call an abstract synthesizer. So the idea, the abstract synthesizer takes the specification, the I/O examples as a Euro synthesizer, but also it takes the domain knowledge encoded as a domain-specific language as well as an abstraction. So the goal of the abstract synthesizer is to synthesize a program that satisfies the specification according to the abstract semantics under the given abstraction. So as I mentioned earlier, the advantage of this idea is that it reduces the search space more significantly. And as a result, the abstract synthesizer is much more scalable. However, the fact that the abstract synthesizer returns a program that is consistent with the specification according to the abstract semantics does not really imply that the return program is actually correct according to the concrete semantics. In other words, the abstract synthesizer may return spurious programs. Let me show you an example just to illustrate. So let's say we have example that the specification 3 goes to 6, and we are working with an abstraction with 3 abstract values. These are intervals, so 1 to 10, 11 to 20, and 21 to infinity. So by the way, I should say that this abstraction is a specific set of specific intervals. Here, we basically have a specific set of concrete intervals here of size 3. So using this abstraction, we're going to partition the program space into 3 disjoint sets, depending on their abstract output value. So now here, we know that the output example 6 does not really belong to the 2 intervals on the left. So we're going to reject all the programs in these 2 partitions. However, the synthesizer, the abstract synthesizer, is free to return any program whose abstract output is the interval, the range 1 to 10. For instance, it may return a program, x plus 2, which doesn't really satisfy our specification. In other words, this is a spurious program. Okay, now, because our abstract synthesizer can produce spurious programs, our approach iteratively refines the abstraction in order to guide the search for the desired program, the correct program. So in particular, given the current abstraction as well as the spurious program, our approach automatically constructs a new and more precise abstraction such that under this new abstraction, this program P, this spurious program, can be rejected. Just to explain this, let's say we still work with the same example, the same abstraction. Let's say the abstract synthesizer gives us the program x plus 2, which clearly doesn't satisfy our specification. So our method will construct automatically a new abstraction with new abstract values. Here we have this new concrete interval 1 to 5. So using this new abstraction, our abstract synthesizer will no longer return the spurious program. In other words, the x plus 2, the program, is rejected using this new abstraction. All right. Just to put all these together, we refer to our synthesis framework as synthesis using abstraction refinement. So it takes as input the I/O examples, the specification, as well as the domain knowledge encoded as a domain-specific language and its abstract semantics. So internally, it has 2 very important components. So the first component is an abstract synthesizer, which generates candidate programs that are consistent with the specification according to the abstract semantics. So there is also a refiner, which refines the abstraction, generates new abstraction whenever the abstract synthesizer gives a spurious program. So upon termination, the synthesized program is guaranteed to satisfy the I/O examples of the specification according to the concrete semantics. All right, good. So in what follows, I'm going to explain in more detail the abstract synthesizer and the refiner, starting with the abstract synthesizer. So in order to synthesize such a program, the program that satisfies the I/O examples according to the abstract semantics, our synthesizer uses a method that is based on variance-based learning. So the idea behind variance-based learning is that it constructs a compact data structure that represents all the programs in the space that are consistent with the specification. So for instance, variance-based algebra is such a method that is based on variance-based learning, and the data structure it uses is DAG. So in our case, we construct a finite tree automata. So this is the data structure we are using to compactly represent all the programs that are consistent with the specification according to the abstract semantics. So just a few more words. So the idea of synthesis using finite tree automata was actually first proposed in our prior work that was published at Uppsala last year. So the idea there basically is we constructed this data structure, this FTA, using the abstract semantics. That is, the states in the automata correspond to concrete values of the programs. And the transitions are constructed using concrete semantics of the DSO constructs. So here in this work, in our POPL work, we fully generalize this method by basically constructing an abstract finite tree automata using the abstract semantics of the language. So that is, the states in the automata now are corresponding to abstract values of programs. And the transitions are now constructed using the abstract semantics of DSO constructs. Okay, so as a result, so the size of the data structure of the FTA now is much smaller, and therefore our abstract synthesizer is much more scalable. So yeah, due to the time constraints, I'm not able to explain more detail to you, but if you are interested in this, please read our paper. Okay, so now let's switch gears and see how our abstraction refiner works. So recall that the abstraction refiner takes as input the spurious program as well as the current abstraction, and returns a new and more precise abstraction, such that this spurious program can be rejected using this new abstraction. And the key idea here is to guarantee that we can obtain such a new abstraction is by constructing a so-called proof of incorrectness for this spurious program. And the new abstraction basically will include the abstract values that are used in the proof. So now I'll explain more. So first of all, the definition, the informal definition of this proof. So given the example I goes to O, as well as a spurious program, P, that is represented as an abstract syntax tree, the proof of incorrectness for this program P, the spurious program, is a mapping or annotations, if you wish, from P's AST nodes to abstract values, new abstract values, such that the following two conditions hold. So the first condition is the proof maps the root node in the AST to an abstract value A, such that the output example, the desired output, is no longer in the concretization of this abstract value A. And the second condition is the annotations in the proof, the abstract values at the AST nodes, are correct with respect to the abstract semantics. So intuitively, the second condition says this proof is valid. It's a sound proof. And the first condition further states that using this proof, we can prove that this program P is incorrect, which we couldn't really prove using the previous abstraction. All right. So as you can also imagine, there might be many such proofs, many valid proofs to prove this P is incorrect. And we want to find a general proof. So that is the proof, the abstract values in the proof are weakest or general, if you wish. So the advantage of having a general proof is that it can prove the incorrectness of more programs, many more programs, beyond this specific spurious program the refiner is looking at. So this way, the new abstraction is likely to reject more programs in the next iteration. Okay, so let's see an example. So let's say we have a spurious program. This is just the old program we just synthesized, x plus 2. And our example is 3 goes to 6. So this program doesn't satisfy this example clearly. Now we're going to have a proof. So this proof, this proof, I just want to emphasize 2 points. So first of all, this proof is a valid proof. It proves the incorrectness of this program because the sum of x and 2 is in the range 1, 5. And the output example 6 is no longer in this range 1, 5. And the second point is this proof is general because it not only shows the incorrectness of this specific program, or like the program that produces the programs that produce the value 5, but also other programs that can produce any value in this range 1 to 5. All right, so this is enough technical detail. Let's look at our implementation. So we have implemented our proposed ideas in a tool called Blaze. So it's here, which can be instantiated to any domain by providing 3 things: the DSL, the domain-specific language, a set of abstract values, and also the transformers. So a few more words. The DSL is basically in context-free grammar. Now we're assuming basically this DSL is functional and it is just loop-free without recursion. So for the abstract values, these are we're basically doing predicate abstraction. So we're using the abstract values are conjunctions of atomic predicates coming from a predefined universe, and the atomic predicates are specified using templates. So the abstract values are used in the refiner to construct the proof. So we also have transformers one for each DSL construct. And transformers are used in both places, both the synthesizer, the abstract synthesizer, and also the refiner. So let's move on to the evaluation. So we want to answer 2 questions in our evaluation. So the first question is, how does Blaze, how does our tool compare against existing handcrafted domain-specific synthesizers? So to answer this question, we compared Blaze with FlashFill, which is a widely used synthesizer that specifically targets on automating string transformations. And the second question we want to answer is, how does Blaze compare against other meta-synthesizers, other synthesis frameworks? So to answer this, we compared Blaze with Prose, which is a state-of-the-art synthesis framework or meta-synthesizer that is developed in Microsoft. So let's look at our first application domain, the string transformations. So in order to use Blaze, we need to first instantiate Blaze to the string domain. So we need to provide 3 things. So we just directly take the DSL using FlashFill and use this in Blaze. And the abstract values, as I mentioned earlier, is we use conjunction of atomic predicates, and the predicates are specified using templates. So for instance, we have a template here that basically talks about the length of the string, of the string. And also we have another template that talks about the character at a certain position of the string. We have transformers, one for each DSL operator and each predicate template for the argument. For instance, there is a concat operator, which basically does string concatenation in the DSL in FlashFill. So the transformer looks like this. What it does basically is, if I know the input string, the length of the 2 input strings, I know the length of the output string is the sum of the length of the 2 input strings. All right. So this is the result. So we compared Blaze with FlashFill over all the string transformation benchmarks from the SYNGAR dataset. And the upshot here is we can solve more benchmarks in less time. So in particular, Blaze solves 90 benchmarks out of 108 in about 0.5 seconds on average, whereas Flash solves 87 benchmarks in about 7 seconds on average. All right. So let's move on to the next application, the next matrix transformation. So just a few more words about this. So this is matrix transformation is a very common task in MATLAB. for MATLAB users, which involves transforming one matrix to another. And for synthesis, this is really challenging because the search space is very large. If you imagine it's basically, this is because the matrix or in general tensor is a very complex data type. We also instantiate Blaze to the matrix domain by providing the DSL abstract values as well as the transformers. So we're using a subset of MATLAB, and we're still doing predicate abstraction, and we're writing one transformer for each DSL construct, as well as the predicate template. We have compared Blaze with Prose on 39 benchmarks collected from MathWorks and Stack Overflow. The takeaway message here is that Blaze can scale better than Prose for large search space. So here, as we can see here, Blaze solves all the benchmarks in an average of 3 seconds, and this outperforms Prose on average by 2 orders of magnitude almost. So these 2 experiments show that the idea of using program abstraction and also abstraction refinement is very helpful to scale up synthesis algorithms. All right, so with that, I'm happy to take questions.
So there was a CSL paper which does the recursive programs on finite domains that you know about, right?
Yeah.
So I was wondering whether you could apply it to not just expressions, but also recursive expressions.
I'm sorry, for apply to what?
For programs which have recursion in them as well.
Oh.
Because the main assumption I think that you're using is that the abstract domain is a finite number, right? Finite. That's why how you're building the finite automata, right?
Yeah.
So, and this would work even with recursion because it'll just go to a fixed point, right? You'll compute the least fixed point and it'll work too. So I was wondering whether that would work.
Yeah, in my work, we actually have been thinking about this. The main problem here is, the problem basically comes from the Apple synthesizer part. So we're using a particular method based on FTA. So the way we construct this, basically, it doesn't really handle recursions. The way we think.
But the CSL paper does.
Oh yeah, so if we can, basically if we can replace our method with the method that can use recursion, that can handle recursion, right, then this is doable, definitely.
I have not understood with respect to which space you refine, because by the Ranzato-Giacobelli theorem, the refinement must be with respect to the most concrete semantics.
I'm sorry, could you just repeat?
I have to say that, otherwise, when you refine, you have an abstraction, you refine with respect to some more concrete abstraction.
Yeah.
So with respect to what your refinement are done. Because, for example, for the interval, you look to cut the interval in pieces, and this is incomplete. That is, you may have to refine to relational domains, for example.
Are you saying...
I will ask you my question between us, so you have time to think.
Oh. Yeah, sure. Let's take this one. Yeah, sure.